Hello there. In this video we're going to look at population change models and what happens when we start fiddling with some of the parameters. So we're going to start with this generic rule that next year's population is the current year's population times 1 minus d, and d is going to be the decay rate. So maybe your decay rate's 1%, so you do 1 minus 0.01 or 0.99 times now, which you have left. Plus r will be the restock value, and the starting amount will be I for initial value. So let's look at what happens to the long-term population, and I'm going to use S for where this stabilizes. Okay, so we'll write the equation. Now the nice thing is that wherever it stabilizes, the next year's population is equal to the current year's population. Now, this needs to be mentioned here that this S, assuming that it stabilizes at all, is actually a pretty major assumption. So before you run ahead and always use this type of formula, you do need to convince yourself that it will stabilize somewhere. That's pretty important. Okay, so we're going to try to solve for where that S does stabilize by isolating the variable. And on the left-hand side, I can factor out an S. Start reducing what's inside. And divide. So this long-term stabilization place, whatever it might be, assuming it does stabilize, is equal to the restock value divided by that decay rate. So say we put in like 1,000 fish, and we only lose 1% per year, so that's 1,000 over 0.01. Or, in the long-term stabilization, would be 10,000 fish. Now, the kind of key thing here to note is that this long-term stabilization point has absolutely nothing to do with the initial value. So I could double the initial value, I could have it, I could triple it, as long as you don't create some sort of degenerative case where it won't stabilize. Your long-term stabilization, this number is not important for what it is, only restock and the decay rate. It does bear to mention here that this is important for determining, this can be important for determining whether or not it stabilizes, so you always have to check that kind of thing. Okay, let's delve into some special cases now. So we know that the long-term stabilization rate is going to be at the restock value divided by d. What happens if I double the restock value? Or more specifically, I put some scalar on the restock value. Maybe I triple it, maybe I have it, maybe I quintuple it. So some scalar times k. All right, we'll do the algebra. And when all of that is said and done, I wind up getting kr divided by d. Or in other words, k times r over d. So this stabilization, the old stabilization rate was r over d. Here it's r over d, then multiplied by k. So what this means is if I double the restock value, I will double the stabilization point, or the long-term population. If I have it, I'm going to have the long-term stabilization amount. If I quintuple the restock value, I'm going to quintuple the long-term population. So that's kind of neat. All right, one more of these. What if I apply the scale factor onto the decay rate? So same as the initial setup here, but now I got 1 times k decay rate, S, plus the restock value. So maybe the original population decrease was 1%, and now that's going to increase to 2%. I'm doubling that decay rate. Working through the algebra here. And when all is said and done with this one, I wind up getting r over kd, or r over d times 1 over k. So the long-term stabilization seems to be inversely related to that decay rate. So if I double the decay rate, I'm going to have the long-term stabilization. If I quintuple the decay rate, so we're losing like 5 times as many people, I'm going to cut the long-term stabilization rate amount for the population by, what's that, a factor of 5 then. So that's kind of a nice algebraic way to convince yourself of these relationships. Double the restock, double the long-term population. have the decay rate double the long-term population. But all of this hinges, once again, on the assumption that it does stabilize somewhere. So you always need to convince yourself that this does go to a certain number, that it's not going to spiral off to infinity. You got to jump through that hoop first. Okay, thanks for watching Character and Scholarship for Life.